Hello, and welcome back to Greg Does Physics. My name is Greg, and on this fine Friday afternoon, I'm going to be doing some physics. To close out the week, we are going to be doing problem 1.62 from Griffiths E&M. And it says, the integral A, which we define as the surface integral of dA, is sometimes called the vector area of the surface S. If S happens to be flat, then the magnitude of A is the ordinary scalar area, obviously. We will be starting with part A, which asks us to find the vector area of a hemispherical bowl of radius r. So, to write out my hemisphere, I'm going to just use it as sort of the top half of a sphere, which is centered at the origin. This will make our math a lot easier when we do it this way. So then, what is dA? Well, for a sphere, or for the surface of a sphere, dA would look like this. R squared, whatever the radius of that sphere is, so capital R squared, sine theta d theta d phi r hat. So this is our element of area for the surface of a sphere. Now, looking at A, we can see that if we are going to calculate this vector area for the sphere, we would have r squared sine theta d phi r hat. Easy enough to calculate out, right? Well, not quite, because if you watched my prior video on problem 1.38, I believe, or if you're just familiar with spherical coordinates, then you'll know that this r hat, the unit vector in spherical coordinates, is not constant. It changes its direction depending on where you are in space. And so we can't just pop this r hat out of the integral. So to calculate this integral, what we should do is we should write this r hat in terms of things that we can integrate and or are constant, like Cartesian coordinates, Cartesian unit vectors, because the Cartesian unit vectors x hat, y hat, and z hat are constant. They always point in the same direction anywhere in space. And so if you watched again that same video on spherical coordinates, I calculated that problem asks you to calculate r hat in terms of the x hats, y hats, z hats, and then theta and phi. And so using that result from problem 1.38, I believe it was, which is this, r hat equals sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat, we can plug this in for r hat, and then suddenly this integral becomes doable, and we just have to integrate each element, x hat, y hat, and z hat, over theta and phi. And so let's write that out. So we can pull the r squared out, and I'll do an x hat. So this would be sine theta times sine theta, so sine squared theta d theta, and that's 0 to pi, and then 0 to, actually, it's not 0 to pi, because since we're doing a hemisphere, we go 0 to pi over 2. But our azimuth length still goes all the way around 0 to 2 pi. And so we have cosine phi d phi. So that is our x hat component. Then y hat, 0 to pi over 2, are polar angle terms. So sine theta times sine theta, again it's sine squared theta d theta 0 to 2 pi sine phi d phi. And then finally our z hat component 0 to pi over 2. And it's going to be sine theta times cosine theta sine theta cosine theta d theta 0 to 2 pi d phi, because there are no phi terms. So this looks right to me. Yeah, it should be right. And so, okay. Now just to calculate this. So remember, if you integrate a sinusoid over an entire phase, so for example, you integrate sine from 0 to 2 pi, then it's going to end up being 0 because the area above and below cancels. Above and below, well, if we say this is y equals 0, it cancels. And likewise with cosine. And so we automatically know that our y hat term and our x hat terms are going to go to 0. And so what we're left with is a z hat term, and we're left with r squared, and this, we can also do this integral, so 2 pi r squared z hat integral from 0 to pi over 2 sine theta cosine theta d theta. And that integral, I wouldn't say it looks great, but we can do this integral, we can sort of work around doing this integral if we use integration by parts. And so I'll put that up here, integration by parts. And so we can say that this integral is 0 to pi over 2 sine theta cosine theta d theta. So doing integration by parts, what we want to do is we want to define a function f and a function g, and what ends up happening is we can sort of switch the differentiation around, pick up a boundary term, and then that makes this easier to solve. So if we define our function f as this term on the left, then we say function f is sine of theta, and then we say that this term is the differentiation with respect to theta of some function g, which of course would also just be sine theta. So then what we do is we have negative integral 0 to pi over 2, and like I said, we switch the differentiation around, and so the sine of theta, we would derive that, so it's df d theta, and that would be cosine theta. And then if this is dg d theta, then we want to multiply this by g, which is sine theta d theta, and then we pick up a boundary term, which is just f, the functions f and g multiplied together, evaluated over this interval. So that's sine squared theta evaluated from 0 to pi over 2. But you'll notice that these two integrals are in fact the same. And so what we can do is we can take this, and since this is negative here, we can add it to this side, and we end up saying that this is the same as cosine theta sine theta d theta, and then we divide this side by 2, 1/2 sine squared theta 0 to pi over 2. So normally with integration by parts, you would actually solve this out, but it just so happens to work out that these are the same, and it lets us like not calculate this integral directly, but sort of work around it and still end up being able to solve it. And so sine of pi over 2 would just be 1. We square that 1, then we get 1/2, and then sine of 0 is of course 0, so it's just 1/2 minus 0, 1/2. So our integral is 1/2, which means we can go back here, say this is 1/2, and thus our vector area A for the hemisphere is pi r squared, pointing in the z hat direction. Now, does this make sense? Yes, it does. Because if you think about what these DAs are, they cover an infinitesimal patch on the surface of the sphere, and they point radially outward. But if we were to integrate over the surface, that is, we add up all these patches of dA over the surface of this hemisphere, then what we're going to get is all the components in the x hat and y hat are going to be canceled out by the patch that is exactly on the opposite side. So this patch and this patch of dA are going to cancel out in x and y, but they'll add up together in z hat. They conspire in the z hat direction. And that's why, so it makes sense that our x hat and our y hat terms went to 0, and we only end up with a z hat term. And this pi r squared almost sort of looks like we're looking downward on this hemisphere, and all we see is projected in this xy plane a circle. Because the circle, this circle here at the boundary, would have an area of pi r squared. And so then you might be asking yourself, is that just a coincidence? Is there more here? And we'll find that it is not a coincidence as we go on with this problem. So now that we've solved that for part A, let's go to part B. And part B asks us to show that the vector area equals 0 for any closed surface. Hint, use problem 61A. Now, I have not put a video up for problem 1.61 yet on this channel, but I think I will. That'll be forthcoming. But we're just going to use the result from problem 61 part A, and luckily the problem statement for 61 part A already gives us that result. And so I'm going to erase this just so we have a little bit more board space to work with. So, and we're back. I left our result from part A up here, but let's write out the equation we want to use that comes from problem 61 part A. And that is going to be an integral over some volume for the gradient of a scalar function t times some volume element equals the closed loop integral over the surface that encloses that volume for that scalar function t. Now, you'll notice that the way we defined our vector area is to be the integral of a surface, dA. But if the problem, part B, wants us to specifically look at what is the vector area for a closed surface, and this is an integral over a closed surface. So this looks a lot like this, except in this case, t equals 1. And so then what we can say is we can say that if A equals a closed loop surface dA, then that would be the same as this integral, this volume integral. Except what this is the gradient of the number 1, which is the gradient of a constant. And the gradient of a constant is, of course, 0. So it's 0. Alright, there we go. Easy enough. Let's move on to part C. So, part C asks us to show that A, the vector area, is the same for all surfaces sharing the same boundary. Now, I quite like this part of the problem in particular because I feel that Griffiths sometimes has a problem where he will give you a problem that might be not immediately obvious how to solve it, or might take some sort of lateral thinking rather than just applying like the tools that he's given you directly in the way that he shows you how to use them. And so in such instances, oftentimes he'll just give you a hint that basically explains how to do what it is he's asking you to do. But with this part of the problem, I think he could give you a hint, and yet he doesn't. So it might not be immediately obvious how to think this one through and how to do it. And funnily enough, you know, the tools that it takes to do this one are actually in the problem itself. It might not be immediately obvious, but in fact, this is the kind of problem where every subsequent part of it is built from the prior ones. And Griffiths doesn't directly say that. And so I actually do like this problem, because you have to sit and think about what it is you found in the problem so far and use that to do the next step. And that might not be obvious at first. And so let's specifically think about part C. It says, we want to show that A is the same for all surfaces sharing the same boundary. So let's just say that we have some surface like this. This is our surface. It has a patch dA. And this right here is its boundary. But let's say we have another surface that also has this same boundary, so it'd be kind of like not perfect, but let's imagine that these two boundaries are the same. And the surface, it doesn't have to be the same. It could be kind of like that. So you imagine that this is sort of like some closed surface that kind of wraps around and has this part opened down here. So this would be the boundary for this surface. And if we're saying that these two boundaries are the same, then in principle, how do we show that these two things have the same vector area? And to do this, we kind of got to think a little bit topologically. And this is the point where if you've taken a topology class or you have any exposure to topology, that might help you out here. If not, you don't necessarily have to. But let's think about this. If you have two surfaces which share the same boundary, and they don't have to be in a similar orientation like that, in principle, couldn't we take the two surfaces, whatever the surfaces themselves are, as long as they have the same boundary, couldn't we orient them in such a way that we sort of stick them together at the boundary? So say we take this surface on the right and we sort of flip it upside down and we plug it up here so that this boundary perfectly matches on to this boundary. It'd be like taking two hemispheres, like we have this hemisphere and we have another surface with a circle as its boundary, and we just pop the two circles together. And what that would give us is it would give us a closed surface, because now we have just total surface on either side. There's no boundary there because it becomes a closed surface. And so what we've done is we've taken two surfaces which had the same boundary, we stuck them together in such a way that now we have a closed surface. But if we have a closed surface, we've already established that the vector area of a closed surface is 0. And so if the if the vector area of a closed surface is 0, then that should indicate that these must be equal. Because let's say that we have two structures who have a vector area that aren't equal. So say this is A1 and this is A2, and they're not equal. But if they're not equal, then when we calculate the vector area for the combined surface, it would look something like A1 minus A2, which would not equal 0. But if it doesn't equal 0, then that doesn't follow with our discovery, our claim, that a closed surface has a vector area of 0. So they have to have the same vector area. And that's how we would show that. Part D. Show that A equals 1/2 R cross dl, where the integral is around the boundary line. Hint: one way to do it is to draw the cone subtended by the loop at the origin. Divide the conical surface up into infinitesimal triangular wedges, each with vertex at the origin and opposite side dl, and exploit the geometrical interpretation of cross product, figure 8. Now, figure 8 looks like this. So figure 8 is this. We have a vector A, a vector B. They have some included angle theta. And it's saying that the magnitude of the cross product, A cross B, would be the same as the area of this parallelogram, because the magnitude of the cross product would be A, B, the magnitude of A times the magnitude of B times sine of theta. But that would just give you the magnitude of B times the vertical, the component normal, the component of A normal to B, which just gives you the area of this parallelogram that's created. Okay, so how are we going to use that in tandem with this? And let's think about the hint that Griffiths has given us. It says one way to do it is to draw the cone subtended by the loop at the origin. So let's say we have a surface like this. This is our surface. And we want to calculate the vector area of this surface. So one way to do it is to draw this cone subtended by the loop at the origin. So let's say that we would have create a cone by taking on this boundary, at every point on this boundary of this surface, we draw a point back to the origin. And what we'll get is we'll get something that sort of resembles a cone. It'll have ridges and whatnot, but it'll resemble a cone in principle. And what we can imagine is we can label each point for a given point on this boundary. This is R, and the point that the infinitesimal vector that points in the direction of that boundary is dl. And so then what we can do is we can look at it like this. We can take an infinitesimal triangular wedge of this cone, and what you would get is you would get something with that looks like this. And so these are the infinitesimal triangular wedges that Griffiths is calling attention to. So this is R and this is dl. But if we look back at our geometrical interpretation of cross product, then what we'd be saying is that the area of this triangle, knowing that the area of a triangle is 1/2 base times height, the area of a parallelogram is just the base times the height. And so hence we could say that the area of this triangle this infinitesimal triangular wedge is 1/2 times the magnitude of the cross product of r and dl. Because what that would give you is that would give you the magnitude of this position r times the component of dl, which is normal to it, and multiplying those two together already would give you the area of the parallelogram created by them but doing 1/2 would give you the area of the triangle that's created by them. And so then what you can imagine is that you can imagine at every point along this boundary we take our r and then we take some infinitesimal dl, and doing this cross product times 1/2 gives us the area of that triangle. But then if we were to add all these infinitesimal triangular wedges up all the way around the boundary, that would give us the total vector area, provided we take the magnitudes off this cross product, because what the vector area actually is summing the dA vectors, and so we do want the direction that comes with cross product, because that would be the direction of the dA in this case. And so what we're doing is we're adding the dAs, the areas, the vector areas of each of these triangular wedges all the way around this boundary until what we get is the vector area of this cone. The cone that's created by subtending the boundary of whatever surface we're looking at to the origin. And so then the final jump here now is that we've showed that at least for this cone that we've created, we're confident that integrating this cross product of r and dl times 1/2 gives us around this closed loop here, the perimeter of this surface, gives us the vector area, okay? But how does it show us that this is the vector area for our initial surface? And again, all we have to do, much like in part C we looked back at part B, what we have to do here is look back at our result for part C, in which we claimed that the vector area of two surfaces is the same if they have the same boundary. But of course, this cone that we've created is going to have the same boundary as our original surface. And so there we can say that this equation that works for the cone must also work for the surface in question. And so there we go. That is how we would show that this equation holds up. Okay, and that will finally bring us to part E, which is show that we want to show that the closed loop integral of some constant vector dotted with the position vector dl equals the cross product of our vector area and the constant vector in question. And so then Griffiths gives us a hint: let t equal c dot r in problem 61e. And so we're going to go back to problem 61, like I said, video on that forthcoming, but we're going to use the result from 61 part E. And that, luckily, again, is given to us in the problem statement, and that is a surface integral of the gradient of some scalar function t crossed with dA equals negative closed loop integral around a perimeter of that scalar function t dl. And we're saying that t equals the dot product of c and r. Alright, so let's just plug this in. So we get vector, so the gradient of c dot r crossed with dA equals minus close to the pinnacle around the perimeter. C dot R. Okay. Fair enough. So then what I can do is we could put a negative on both sides and then flip this cross product around. So then what we can do is dA Okay. I'm going to erase this side of the board to give myself a little bit more space. So let's focus on this term right here, the gradient of C dotted with R. Now what we can do is we can return to our product rules and expand this. And so from Griffiths, I'm going to be using product rule, let's see here, 2, which is the divergence of A dotted with B would be the first vector, C in this case, crossed with the curl of R in this case, and then flip it around, R crossed with the curl of C. And then we add C dotted with the del operator R plus R dotted with the del operator C. And so instantly we can see this one, we're taking the curl of a constant vector, which would be 0. This term, we're taking the curl of the position vector R, which also would be 0, because there are no cross terms. It's just R hat. And so thinking about a function that's going entirely radially out from the origin, that's probably not going to have a curl, and in fact, it does not have a curl. So that goes to 0, and now we have these terms. Now, if you're doing this problem on your own, this is a part where you have to be careful. Because if you're familiar with dot product, then you know that dot product is commutative. So, for example, if we had the dot product of A and B, that would be the same as the dot product of B and A, like this. And so you might be tempted to look at this and say, oh, this is just the same as the divergence. This is just the divergence of a constant vector, and therefore it goes to 0. But we need to be aware of is that the del operator is not a traditional vector. It looks and acts like a vector a lot, but it is not a true vector. And so this commutative property of the dot product doesn't actually hold up when one of our vectors is the del operator, because it's an operator. And so if we're going to, for example, do this term, C dot the del operator, then in Cartesian coordinates, that would be Cx ddx plus Cy ddy plus Cz dz. And you can see how the terms from the constant vector are on the other side of these partial differentiations. And so since they're on the other side, it's not the constant vector's components that are being differentiated. What's going to be differentiated is in fact going to be the vector r. And so if we look at this second term over here, it's the same thing. So it'd be, for example, d dx plus y dy plus z dz, and then times the constant vector. But then when we distribute this, it would be x dx times the constant vector, y dy times the constant vector, z dz times the constant vector. And in those cases, then we'll be differentiating this constant vector, and then it would go to 0. So even though it looks like even though our first instinct might be to just flip this order around and say, this is the divergence of a constant vector, it's 0. This is the divergence of the position vector r, that's going to be 3, I think. Then that is wrong to say, because like I've said a few times, the del operator is not a normal vector, and you can't just use this commutivity. And so basically what that says is that this right here, this quantity, the gradient of c dot r, ends up just being this term, c dotted with the del operator times the position vector. And so what that would look like is the x component, what we get is we get cx ddx, and the x component would be xx hat. So ddx xx hat, you would just, the x goes to 1, the x hat is constant, so that comes out. Of course, the y hat and the z hat components of the position vector don't have any x components or x's in them, so those would go to 0. And so it follows this form that we would get cy y hat c z z hat, which of course is just our original constant vector. And so then looking back at this equation now, what we're going to say is that this is s dA crossed with c, and that equals this closed loop around the perimeter c dot r dl. But since this c is constant, we can imagine that we can sort of take it out of our integral, because it's constant, and what we're left with is this integral over a surface of dA, which is just our original definition of the vector area A. So this becomes A cross C equals and looking back at this equation, this is exactly what we were asked to find. And I believe that that is the final part of this problem. Indeed it is. So yeah, that is problem 1.62. I actually really like this problem just because, like I said, it makes you think. Griffiths just doesn't instantly give you all the tools and say, do what I do. You have to actually take a step back, and when you're thinking about, I mean, he does kind of give you the tools for like part B and part E, for example. You have to do a little bit of thinking, and this part can be tricky, but it's a good reinforcement of the fact that you can't always just treat the del operator as a normal vector, because that'll get you in sticky situations, like just assuming this is the divergence when it's not. But other parts of this question I do like, particularly the part where you have to prove that two surfaces with the same boundary share the same vector area, and that just rests on a little bit of topological thinking and then using the results you've gotten from earlier in the problem, even though Griffiths doesn't explicitly make it clear that that's what you should do. It could be easy to just get lost looking back at like Green's theorem, Stokes' theorem, all the different identities that had been introduced up to this point, and just being bogged down and going, where do I solve this? Where do I get the tools to solve this? And really, you just have to take a step back and think a little bit topologically, think a little geometrically about how you can orient two surfaces with the same perimeter together, create a closed surface, and then that tells you that they have to have the same vector area. And in fact, I also like that result because suddenly it illuminates earlier on in the problem. Like, for example, in part A, we said that the vector area is pi r squared z hat. And if we're saying that that is the same for any surface with this boundary, well, what's another surface with this boundary? It would just be a circle at the origin with radius capital R. And of course, like Griffiths says in the beginning of the problem, what are the words that he uses? He says specifically, if S happens to be flat, then the magnitude of A is the ordinary scalar area, obviously. And this makes it a lot more clear why that is. Because if two shapes share the same boundary, then of course, in this case, we can blow up, a surface around this perimeter here and do whatever stuff we want with it, but it is always going to be the same vector area as just the flat circle, at least in this specific case. And so suddenly our discovery that this has pi r squared in the z hat direction as its vector area, then that makes a lot more sense here for a flat circle, because of course the area of a circle is pi r squared. And so I just like this question because even though it might not be like, okay, this is, this is like pretty broad, this isn't, how is this applied to electrostatics and whatnot, but I think just in terms of getting you to think about these concepts, to think some of these things through and see how different parts of this question connect to each other, I do think it's a good question for those reasons. And I hope that this long walkthrough helped you. So thank you so much for watching, and I will see you next week.